This video is going to be about terminal speed of a falling sphere. So my sphere is going to be falling through a viscous fluid that's inside this container. The forces acting on my sphere are going to be its weight pulling it downwards, the buoyancy force acting against the weight, and the drag force. Now the drag force is going to increase with the speed of the falling sphere until it reaches something we'll call terminal speed. And the reason it reaches terminal speed is because the drag, the buoyant force, and the weight sum to zero, meaning there's no net force acting on the sphere, so it no longer accelerates. Therefore, it continues falling at a constant velocity, which we once again call terminal speed. We can use Stokes' law and Archimedes' principle, Archimedes' principle, to find the terminal speed of our falling sphere. So we know that the buoyancy force plus the drag force, which are acting upwards, so those will be positive, minus the weight of our sphere, which is pointing downwards, so it'll be negative, all of these sum to zero. Our force of buoyancy is equal to the density of the fluid times the volume of our sphere times the acceleration of gravity, plus, then Stokes' law will give us the drag force, so 6 pi times the viscosity of our fluid times the radius of our sphere times the speed of the sphere, the sphere is going, minus mg, which is the weight, is equal to 0. Now the speed in this equation, because this is the speed when all the forces will sum to 0, is our terminal speed. So that's what we'll solve for. So I'm going to isolate the speed, and I'll move everything else to the other side of the equation. So I end up with the weight minus this term which describes the buoyant force divided by 6 pi viscosity times the radius of our sphere. Okay, so we could stop there, but we could also simplify this equation by expanding out the mass of our sphere into density and volume. So we have the volume times the density of the fluid times gravity minus the density of our fluid times the volume of our sphere times the acceleration of gravity divided by 6 pi times viscosity times the radius of our sphere. Now the volume of our sphere and the acceleration of gravity are constant, so now I just take the density of our sphere minus the density of our fluid, because I factored out everything else, divided by 6 pi viscosity radius, and I can expand out the volume here into the volume of a sphere, 4/3 pi r cubed, okay, times acceleration of gravity, and everything else in the equation stays the same. All right, I see that I have pi on the top and pi on the bottom, so that'll reduce. I have r squared on the top, and r cubed on the top, and I have 1r on the bottom, so I can reduce r to r squared. And I can also divide 6 into 4/3, and in the end I get 2r squared times the acceleration of gravity divided by 9. So I got the 2/9 by dividing 6 into 4/3. And my viscosity stays on the bottom, times the difference in our densities. So the density of our sphere minus the density of our fluid. All right, so that is how you can find the terminal speed of our sphere using Stokes' law. This will only work for a sphere because Stokes' law only applies to spheres. All right, that's the end.